How many Faraday of electricity is required? How many Faraday of electricity is required for the electrolysis of this and that? And there will be a nearly and different types of problem is present here. For all of them, you are going to adopt the same procedure. First, you should consider which species is undergoing oxidation or which species is undergoing reduction. How many electrons are required for completing 1 mole of that reaction, either oxidation or reduction. And from that equation, you can calculate how many Faraday is required for the complete electrolysis. That is either to be oxidized or to be reduced. You can easily calculate this one. Then from first you find out the relationship between the 1 mole of the compound and how many Faraday. I'm going to explain this. Then what is asked? Whether how many moles are they are asking. For that moles, how many moles of electrons, how many moles of Faraday would be, I'm sorry, how many Faradays would be required. You can easily calculate it. Or how many electrons are involved in the following electrolysis reaction, or how many moles of electrons are involved. These are three types of problems are following the same procedure. With one example, I am explaining this. Then you can automatically give answer for other types of problems. And for example, how many Faraday of electricity is required? How many Faraday of electricity is required for the reduction of Mn2O3 to Mn2 plus for the reduction of 0.3 mole of 0.3 mole of Mn2O3 to Mn2 plus, for which first we are going to write down the equation Mn2O3 giving Mn2 plus. First balance, as usual, balance this one. And what is the oxidation state of manganese is here? What is the oxidation state of manganese? You can easily calculate this 2x plus this -6, or for each oxygen -2, 3 oxygens is equal to 0. Therefore, x is equal to +3. Therefore, it is in the +3 state. It is converted into this one. And what is the total oxidation state? +6. Here in this side, total oxidation is +6. In the product side, it is +4. Therefore, for this purpose, how many electrons are involved? 2 electrons are involved. For 1 mole of, if you take 1 mole of the electrolysis of Mn2O3, how many moles of electrons are required? 2 moles of electrons are required. 2 moles of electron. If you are asked to calculate how many, this is the relationship used to establish first. After establishing this, then you can give the answer for your question. Here what is asked? For into 3 mole of Mn2O3, you can require a 0.6 mole of electron. And how many Faraday is required? They are asking. The Faraday is nothing but the charge carried by 1 mole of electron, that is Avogadro number of electron, that is equal to 1 Faraday. Therefore, this mole of electron can be replaced by Faraday. Therefore, for the 0.3 mole of Mn2O3 of undergoing electrolysis, 0.6 Faraday of electricity. How many electrons are involved in this reduction process? Sometimes that question may be asked. 1 mole of electron is equal to nothing but 6.023 into 10 to the power of 23. Here, how many moles are required? 0.6 mole. Therefore, how many electrons are involved in the process? These three types of question. Answering this question, first you should establish a relationship for which you should write down the equation and complete the reduction or oxidation, how many electrons are involved. Here, next, the same question, but we are going to give in different format. Here you are given directly 0.3 mole, or sometimes they won't give directly this much amount of the mole is present. Instead, they will give it to you in terms of gram, and then you have to convert the gram into mole, and then once again you proceed with the procedure given, for which I am going to give one sample example. Take down the question. Point is one, how many moles of electrons are required? How many moles of, yeah,
Sir,
yeah,
போன கொஸ்டின்ல வந்து reduction of Mn2O3 to Mn2 plus னு போட்டிருந்தோம் சார்.
yeah.
ஆனா நம்ம பண்ணது ஆக்சிடேஷன் தானே சார் பண்ணோம்.
ரிடக்ஷன் ஆர் ஆக்சிடேஷன் என்ன கொடுத்துருக்கோம்? ரிடக்ஷன் தான் நான் கொடுத்துருந்தேன். Electrolysis change it into electrolysis or oxidation. Reduction, you change this into this process. Sorry.
Okay, sir.
And take down this one. How many moles of electron is involved in the electrochemical change? Change of 0.174 gram of potassium permanganate into Mn2 plus ion. Mn2 plus ion. Here they have given so many gram of permanganate. Sometimes they may given so many gram of permanganate ion. At that time you have to take only this formula weight, not this formula weight. Now we have given potassium permanganate. Therefore you should know the molecular weight of the potassium permanganate. Instead, if they are giving only gram of MnO4 minus, take the formula weight as the molecular weight, for which you should know the atomic weight of manganese, the potassium, and oxygen. If you all combine this KMnO4 would be having the molecular weight 158. Therefore, 0.174 gram divided by the molecular weight, you will get so many moles. Now we have converted the gram into the moles. Then the other formula is similar to this. First, establish the relationship between KMnO4 and Mn2 plus. What is actually taking place? MnO4 minus is converted to Mn2 plus. Here oxidation of manganese is +7. Here one manganese, here also one manganese, okay. Then how many electrons would be involved in the process? 5 electrons are involved in the process. This is a reduction, electrochemical reaction. Therefore, what is the relationship establishment? 1 mole of KMnO4 for reduction requires 5 mole of electron. 5 mole of electron. This is the establishment of the relationship between the mole and the mole of electron, and from which you can be asked to calculate how many Faraday of electricity for 1 mole of KMnO4. So many Faraday of electricity, or 1 mole of KMnO4 on reduction involves 5 into Avogadro number of electron and so on. Here, this is the relationship you have established. Then for this mole, how much would be required? Therefore, this is another kind of problem that can be asked. Third kind of problem, they may suppose it is a gas, or before seeing this gas, I will give you another type of problem. Calculate the number of Faraday or number of mole of electron involved in the conversion of 15 point ml of 0.12 molar permanganate MnO4 minus into MnO2. Last problem we have given in terms of gram, therefore you convert the gram into mole, but here you are given a volume containing 0.12 molar permanganate. From this ml or this volume of the solution should contain how many moles of permanganate? You have to find out. How to find out the number of moles present in 15.8 ml or 1.8 liter of, say, 1.8 liter of 2.5 molar, or you can be also 400 cc. Cc and ml are the same, 0.25 molar, etc. For all the things, the answer is very easy. You simply multiply this and this. What is the volume in which you are going to calculate? 15.8 ml into 0.12 molar. 0.12 molar means mole per liter, that we call is the molar. Here it is necessary to give in terms of mole per liter. Therefore, this per liter and liter gets cancelled. This you know, milli, this is milli, this is mole. Therefore, if you multiply 15.8 into 12.12, you will get millimole. But we are in need of mole. Therefore, in the place of milli, you replace the m with 10 power minus 3. Therefore, now you have got the moles of permanganate present in the given volume and molarity. Therefore, whenever you multiply the volume in milliliter and with the molarity, you will be getting the number of millimoles. Suppose it is given as liter. If you put this 1.8 liter into 0.25 molar, let us assume molar should be converted into mole per liter. Now this per liter and liter cancel. Now the result is directly mole only. Therefore, if you take the liter and multiply with the molarity, you will get the mole directly. If you take milliliter, multiply with the molarity, you will get millimoles. Therefore, after finding out the moles, you can easily, our problem is the previous like problems. Here the milli should be replaced by 10 power minus 3. Okay, now I think you understand the problem. And the last type of problem, what is the other type of problem that can be asked? Asked is, say, in terms of volume of the gas evolved. In that also, you can find out the Faraday and the equivalent. 1 mole of any gas would occupy 22.4 liters. What is asked? What is the volume asked? And you convert into that one, you will get this one. This is the types of problem that can be asked in this. Based upon this, I'm going to give one homework and you can easily calculate this. Then I will go for another type of problem in the electrolysis problem. Take down the question. Calculate the number of electrons involved or number of electrons passed per second to a cross section of copper wire. Number of electrons passed per section to a cross section of copper wire carrying 10 point minus 8 ampere current. 10 power minus 8 ampere current. 10 power minus 8 ampere current. What is asked? Number of electrons passed per second. Therefore, the current is passed for how many time? 1 second. Therefore, the quantity of current passed is equal to I into T. I, the strength of the current, is 10 power minus 8, and the time required is 1 second. If you are asked to calculate the number of electrons passed for 10 seconds, then that place of time T, you put 10 seconds and so on. Now you have calculated. The ampere into second is nothing, but we have seen Coulomb. And how many electrons are carrying this 8 power 10 power minus 18 Coulomb? And you know the relationship. What is the relationship? This 1 mole of electron would be passed. 1 mole of electron would be passed. Then the quantity of electricity is 96,000 coulombs. Or reverse this, if 96,500 coulombs of current is passed, the number of electrons passed is 6.023 or 1 mole of the electron 10 power 23. Here mole of electrons is not asked, number of electrons is asked, therefore number of electrons is asked, therefore I am writing this instead of molar, writing this 6.023 10 to the power of 23 electron. Then 10 power minus 8 coulomb would be carried out by how many number of electrons? That is the way you can easily work out it. Okay, complete the problem in the whole. And then I am going to give another type of problem that may be asked to take down the question. What is the quantity of current required? What is the quantity of the current required for the electrolysis of a dilute solution of sulfuric acid using platinum electrodes to produce 336 ml of mixed oxygen and hydrogen at STP. At STP. At STP condition. At STP condition. Here you are electrolyzing sulfuric acid. But during electrolysis, what you are obtained? The hydrogen at the cathode and oxygen at the anode. Oxygen at the anode. How much amount of hydrogen and how much amount of oxygen would be released? Whenever you know the relationship between these, when one Faraday of electricity is passed, one equivalent weight of hydrogen and one equivalent weight of oxygen would be formed. In this way, you can find out. Or during the electrolysis, sulfuric acid means that is nothing but hydrogen 1 mole and oxygen half a mole is produced. In this way also you can convert this. The water is undergoing hydrolysis. Therefore, 1 mole of water will give you this and this. And what is the equivalent weight of hydrogen? That is 2 hydrogen atomic weight by one சொல்லுவோம் here. 2 is present, therefore equivalent weight in terms of volume 11.2 liters at STP. 1 mole liberates 22.4 liters at 60B, but equivalent weight means 2 hydrogen, sorry, molecular weight by the valence factor அப்படின்னு சொல்லுவீங்க. How to find out the valence factor? The number of atoms present in the valency. That is called the valence factor. Here, the number of atoms present is 2, and the valency of one atom is 1. 2 into 1, it is called as the valence factor. Therefore, equivalent weight is equal to molecular weight by 2. Therefore, 1 mole gives 22.4 liters. Therefore, 1 equivalent weight gives 11.2 liters at STP. And how many liters of this one? The molecular weight divided by valence factor. How many atoms are there? And here, one oxygen atom or molecular weight, half a mole consists of this one. Half a mole consists of one oxygen atom and divided by its valency. You can also calculate in this way, or 1 mole of oxygen would liberate, 1 mole of oxygen liberates 22.4 liters. Here, the valency factor அப்படின்னு சொன்னீங்கன்னா half a mole is there and the valency is 2. Therefore, 1 by 2, the molecular weight, half oxygen atom into the valence factor is 2. Therefore, 5.6 liters, this we have already seen. Therefore, 5.6 liters of oxygen are evolved. Therefore, what would be the ratio of hydrogen and oxygen evolved? If it is 2 times, it will be equal to 1. That is equal to 336. 336 ml. Therefore, of which hydrogen would be 2 times and oxygen would be 1 time. That is equal to 224 ml for hydrogen, and for oxygen 112 ml. Therefore, we have separated how much amount of hydrogen and how much amount of oxygen. And after finding out this is the way you can calculate the individual volume of the hydrogen and oxygen. After finding out this individual, you can make use of any one of the volume to calculate the number of electricity required, making use of V is equal to equivalent weight by the Faraday into the quantity of electricity required. That is I into T, but I into T, they are asking the quantity of electricity. Therefore, I couple it to this Q. Okay, V is equal to equivalent weight by F. Here volume is given, therefore if you use what is the volume in terms of the equivalent weight in terms of volume, you can make use of the volume of hydrogen. If you make use of this volume of hydrogen, then volume is equal to 224 ml. Equivalent weight of hydrogen, 11,200 ml. Here you should, this is ml, therefore here also you should put it in ml. If you put it in the liter here, then you should convert this ml into liter, any of the way, by 96,500 into Q. From this Q you can calculate, from this relationship you can calculate the Faraday of electricity. Okay, I think you understand this problem. Another type of problem is take down the problem. This homework. During electrolysis of acidified water, oxygen is formed at the anode at the rate of 0.224 ml per second. 0.224 ml per second. Compute the strength of the current Passed in the experiment. Passed in the experiment. And so once again, we are going to making use of here volume. It is given therefore V, this formula. And here the strength of the current is asked. Therefore, instead of writing Q, we write it as I into T. Here, what is the time of passage of the current? Here, they are not directly given, but indirectly given. This rate of the evolution is per second. Therefore, in the place of T, you should put the time 1 second. And the volume is 0.2 to 4 ml of oxygen. Therefore, equivalent weight should be given in terms of the volume. You know, 5.6 liter is the equivalent weight of oxygen in terms of the volume. Here it is given in ml, therefore the equivalent weight should also be given in ml. You know the value of F and you know the value T. Now you have to find out the I alone. Take down the option. I is equal to 2.1 ampere, B 3.96 ampere, then C 1.3 ampere, and D it is 2.8 ampere, which is the correct answer. I think you understand the problem and go and work it out. Okay. Then another type of problem in the electrolysis process. Take down the another type of problem. 1 liter of 1 molar copper sulfate solution is electrolyte by passing 2 Faraday of current. Calculate the molarity of copper sulfate solution after electrolysis. After electrolysis. Option A, 0.5 molar. Option B, 0.25 molar. Option C, zero concentration. D, 0.57 molar. The remaining after electrolysis is this much. How to find out this and how to approach this problem? Once again, we are going to use is the weight W is equal to, or W is equal to equivalent weight by Faraday into I into T. Sometimes they will give you I into T, I separately, T separately. Sometimes they combinedly give the I and T as the quantity of the electricity. Here, we have to calculate not the weight of the substance, but we have to calculate the equivalent weight of the substance deposited. That is equal to weight divided by equivalent weight is nothing but we call it as the normality, or so many equivalent weight ne போட்டுருங்க. So many gram equivalent weight is obtained. If you do the W as the gram, it will be called as a gram itself. If you divide it by the equivalent, gram equivalent weight of the substance deposited, then the equation would be converted into 1 by F into I into T. Okay, how many equivalent weight of the substance is deposited? You should know this. Then convert this gram equivalent weight into molarity. You can easily convert this molarity. After this, so much amount of moles have been deposited, then what is the remaining, for which we can easily give the answer. Find out here. You have to calculate the gram equivalent weight, that is nothing but W by QT, 1 by F into I into T. I into T is nothing but the Faraday of electricity passed as given as 2 Faraday. Therefore, 1 into 2F, F and F cancel. Therefore, how many gram equivalent weight of copper has been deposited? 2 gram equivalent. Convert it into mole of copper. Here we have taken in the 1 liter solution, Therefore, we can take it as the normality because so many gram equivalent in 1 mole or 1 liter is called the normality. If you take this 1 liter in the mole of copper, it is called molarity. How to convert the normality into molarity? What is the valency of the copper in this, or how many electrons are required for the reduction? 2 electrons would be required. Therefore, convert this normality into molarity by divided by the number of electrons involved in the 1 mole of reduction 2. Therefore, now the molarity is equal to 1. So much molarity of copper sulfate has been electrolyzed. What is the initial concentration? They have given as the 1 liter of 1 molar copper sulfate has been taken and electrolyzed. How many molarity has been electrolyzed? 1 molar has been electrolyzed. Therefore, what would be the remaining concentration? 0 molar copper sulfate would be present. This is the way you can easily find out. Here 1 liter is given, that is 1 liter of 1 molar copper, but they won't give you in 1 liter. Instead, they would give you in terms of milliliters. And how to convert into liter, then only you can subtract the initial molarity from the molarity after the electrolysis. For which I am going to give one problem and you work out now. Take down the problem. 250 ml of 250 ml of 2 molar copper sulfate. 2 molar copper sulfate solution is electrolyzed by passing 0.75 Faraday of electricity. 0.75 Faraday of electricity. Calculate the molarity of the copper sulfate solution remaining after electrolysis. Here it is not 1 liter of 2 molar copper sulfate, it is given as 250 ml of 2 molar copper sulfate solution. Here we are going to calculate using this solution and using the current 0.75 Faraday, how many moles of copper sulfate has been deposited. By making use of this, we can easily calculate the amount required, but finally you have to convert into 250 ml of the solution. The molarity we are going to calculate is per liter, but convert into 250 ml of the solution. Then only you will get the correct answer. Take down the question, answers option A, 0.625 molar, B, 1.625 molar solution remaining, C, 0.5 molar solution, D, 1.5 molar solution, which is the correct answer. As usual, the procedure is find out the equivalent percent, equivalent weight is equal to 1 by F into the Q. It is number of moles deposited would be equal to 0.75. You can, or also you can do one simplest one, multiply the equivalent weight with the valency here, you will directly get the molarity. Therefore, you can also do this. That is valency or the electrons involved. Anything you can make use. Valency of the ions undergoing reduction or number of electrons involved in the process. You substitute, you will directly get the moles. If you get this weight divided by equivalent IR, moles would be equal to valency, this is equal to 1 by F into 0.75. The 75F is equal to F and F gets cancelled and you will get 0.75 more normality. Sorry, not here we have not put this valency here. Sorry, I will do this in the normal way. So many normalities of time. What is a molarity? Molarity is nothing but the normality divided by the valency. இங்க கொண்டாந்து போட்டுக்கிடுவோம். Normality divided by the valency or normality divided by the number of electrons involved in the process. Copper 2 is undergoing reduction to copper plus 2 electron. Valency is 2. Suppose you are asked to give electrolyzers of the copper plus, then here the normality and molarity is 1 because valency of copper is plus 1. Here if you write this 0.375 molar. Take a note of it. Here we have calculated molarity that is for 1 liter. But the problem given is 250 ml the solution. Only if 1 liter solution is present, so much molar is deposited. And the remaining would be the remaining after the electrolysis. But here taken is 250 ml. Therefore, convert this 1 liter of this molar, that is 1 liter of 0.375 molar, into equivalent to 250 ml into how much molar? This molar volume into molarity is equal to V1 into N1 is equal to V2 into N2. And you are using this relationship in the making use of this relationship in the volumetric analysis. Similar is the case here. Volume V1 here, instead I am using molarity is equal to V2 into M2. Using this problem, we are getting the molarity in 1 liter, but we are using 250 ml as the initial solution. Therefore, this 0.375 when dissolved in 250 ml, what would be the molarity? You have to find out. Therefore, if you find out this, here liter it is given, here 250 ml is there, here also you should put it into liter, 1 into 0.375 by equal to 1 by 4 into M2, or M2 is equal to nearly 1.5 molar. Therefore, in the case of 250 ml solution, you have started with 2 molar solution, but how many molar solution has been electrolyzed? 1.5 molar solution is electrolyzed in 250 ml. Therefore, the remaining solution is 0.5. The option is C. The option is C. If you understand this problem, now work out the problem for in your home and find out the answer. Take down this 100 ml of 0.8 molar copper sulfate solution is electrolyzed for 30 minutes. Electrolytes for 30 minutes by passing 5 ampere current. Calculate the amount of copper sulfate in gram in the solution after electrolysis. After electrolysis. Option A, 4.23 gram of copper sulfate. Option B, 5.37 gram. Option C, 6.14 gram. Option D, 7.28 gram. The copper sulfate, anhydrous copper sulfate, molecular weight is 160 gram. Sir, how to proceed? As usual, how many grams of the copper sulfate has been deposited? Copper sulfate, in terms of molarity, you can easily calculate this. Then convert into 100 ml of the solution, from which you can calculate how many grams, how many molar it would be left remaining, and how many millimoles are there, multiply with 160, the weight in gram would be obtained. That is the procedure. And I think if you follow this is a three-step process. First step, how many moles of copper sulfate has been deposited. Or there is another way you can proceed if you are right enough. Here gram is given. Why can't we make use of this equation, equivalent weight, not in molarity? You can make use of this into 9,360,000 into I 5 ampere current into 30 minutes, convert into second. What is the equivalent weight of the copper sulfate? The molecular weight of copper sulfate is given. Therefore, you can calculate how much amount of this is that taking place. Equivalent weight would be molecular weight by the valency, that is 80. You can put it here 500, and you can make use of this. From this, you can calculate how many grams of copper sulfate has been deposited. Originally, in 100 ml of 100 ml of 0.8 molar copper sulfate. How much gram of copper sulfate has been present? That can be easily calculated. What you should first convert into moles, just multiply the volume and the molarity, you will end up with so many millimole. The millimole is converted into so many mole. Here some value would be there at the end பாருங்க. And 1 mole is equal to how many gram? 160 gram. Therefore, multiply it, you will get what is the original weight of copper sulfate. Original weight of the copper sulfate. What is the weight of copper sulfate deposited here? For the weight of copper sulfate deposited, you should make use of equivalent weight of copper sulfate. If copper is to be deposited, you have to make use of equal weight of copper. Therefore, what is asked in this? In this way also, you can easily calculate this and find out the correct answer. And we will go for the next type of problem in this. Take down the problem. The current efficiency of an electrode deposition of copper, in which 9.8 gram of copper 9.8 gram of copper is deposited by the passage of 3 ampere current for 10 power 4 second, comma, is option A 99%, option B 90%, option C 82%, option D 75%. Sir, so far this type of problem so far we have not solved, but this problem can also be solved. A slight modification in the equation we are going to use. The weight of the substance deposited is X into equivalent weight by the 96,000, that is Faraday current constancy, into I into T. Here, what is X? X is nothing but the current efficiency. This current efficiency, it would be obtained in fraction. Say 100%. So far, no mentioning about the efficiency is given. If no mentioning about the efficiency of the current, you would directly take it as X is equal to 1. Our equation would be changed to our the conventional one, W is equal to equivalent weight for this one. If efficiency is given, you should introduce this X parameter. Here, the X value should be given in terms of the fraction of the current. If it is given 80% efficiency, means X is having the value 0.8. Therefore, if you substitute all the things, you will get a fraction X. But what is given in terms of options or given in terms of the percentage, therefore the fraction should be multiplied by 100. You can easily work out the efficiency of the current. Here the weight of the copper depositor is given 9.8 gram, and equivalent weight of copper, you should know equivalent weight of copper is equal to atomic weight by valency. Valency is 2, atomic weight 63.5. Therefore, 63.5 divided by 2, that is the equivalent weight that can be substituted here. I is given, T is given, W is given. What is asked? X. X would be obtained in the fraction, but if efficiency is given in terms of percentage, multiply it to 100. You go and check the other answer correctly. The answer is the A option. Say, okay, we will go for the next type of problem that may be asked. Next type of problem. Take down the question. A current of 0.193 ampere is passed through 100 ml through 100 ml 0.2 molar 100 ml 0.2 molar sodium chloride solution. Sodium chloride solution for an hour. For an hour. Calculate the pH of the solution. The pH of the solution after electrolysis. Assume current efficiency is 90%. Current efficiency is 90%. And no change in the volume of the solution. The difficulty level is increased. Here efficiency is also, current efficiency is also included. Therefore, here W should be equal to X into equivalent weight divided by 96,500 into I into then T. This is the problem. You have to make use of it. Here, what is asked? Calculate the pH of the solution after electrolysis. For this, you go back to the first class of this electrolysis. On electrolysis of the 0.2 molar solution, not 0.2 molar sodium chloride solution. Take the sodium chloride solution. When electrolysis in cations in the cathode, Na plus and H plus ions are would be there. In the anode, Cl minus and OH minus ions are there. And the preferential discharge potential based upon this, H plus ion would be going on depositing on the cathode or liberated at the cathode, whereas chloride ion, chlorine gas would be liberating at the anode. As H plus ions are removed, the concentration of the OH minus ions are going on increasing. Therefore, after electrolysis, the solution is found to be alkaline. We have been taught like this is not. Similarly, in the case of copper sulfate solution, if you compare this, the solution will be going on acidic in nature. Therefore, when you electrolyze the sodium chloride solution, the pH of the solution is going on increasing. When you acidified and when you electrolyze the copper sulfate solution, the pH of the solution is going on decreasing. to find out the pH of the solution. Sir, how to, for finding out the pH of the solution, here the H plus ions are converted into hydrogen and it is evolving out. But the concentration of OH minus ion is increased. How much amount of OH minus ion would be increased, sir? How much amount of H plus ions are electrolyzed? So much amount of the OH minus is increased, because you know the electrolysis in the ionization process, the water undergoing to electrolyte to equivalent amount of H plus and OH minus. Therefore, how much amount of H plus is converted into hydrogen gas, so much amount of OH would be remaining increase in the concentration. Therefore, our purpose is now you have to find out what is the equivalent weight of hydrogen that is liberated at the cathode. So much amount of OH minus concentration would be increased. That is given by X by Y. We have introduced X because current efficiency is given into I into T. Therefore, it is equal to X is equal to 0.9 because 90% efficiency divided by 96,500. I value is given as 0.193 ampere. T is positive for 1 hour, that is equal to 360 seconds. What is the value of the equivalent of hydrogen liberated? Equivalent weight of hydrogen liberated from the solution. And if you find out this value, you should apply your calculator how to simplify this value. On simplification, you can easily find out it is equal to 6.6 into 10 power minus 3 equivalent weight of hydrogen is liberated. 6.6 in 10 power minus 3 equivalent weight of hydrogen is liberated. Therefore, so much equivalent weight of OH ion concentration is increased. Equivalent weight of concentration is increased. Do you follow? This increase is in how much volume? Go and refer, it is equivalent. This is increased in 100 ml of the solution. Therefore, for the pH determination, you know the POH is equal to minus log of OH minus ion concentration, that is the normality of OH minus or equivalency of the normality means so many equivalent weight percent in 1 liter. But this much amount of OH is increased in 100 ml. Therefore, in 1 liter, how much would be the increase in the concentration of the OH? 6.6 into 10 power minus 2, because you should multiply with 100. Suppose your solution is to be 250 ml. Therefore, convert it to 1 liter, multiply by 4, and according to this, so many equivalent weight, or that is nothing but so many equivalent weight per liter means this is the normality of OH. From this, you can calculate POH. The POH is equal to the POH. From this, you can calculate the POH. Do you want to calculate this POH? The POH would be equal to minus log of the 6.6 into 10 power minus 2. And if you put this minus log of 10 power minus 6.6 plus into minus log of 10 power minus 2 equal to log of 6.6. And what is the value of 6.6? Anybody? Hello, 6.6. Ask your calculator. What would be the value? For 6, you know. For 7, you know. What is the 6.5 from this? Tell me the value. Hello. Nobody else is there. It is equivalent to 0.8. Therefore, what would be the pOH? It is 1.2. But it is not pOH is asked, pH is asked. The options I have not given. Take down the option 7.2, B 8.2, C 10.8, D 12.8. Here look at the options. All of them are in alkaline medium because pH is greater than 7. Therefore, they have given rightly. Okay. Now you can easily calculate what is the pH of the solution. It is equivalent to 12.8. This is the question, but I think so far this type of question is not at all asked. Okay. Then we will go for one question that is asked in the heavily asked in the CSIR examination, and making use after that we will see two more types of problem. Then we will wind up this session. Okay, and you should take down this problem as the homework. Then we will wind up we will see the two more types of problem. Electrolysis of 200 ml of electrolysis of 200 ml of aqueous copper sulfate solution, aqueous copper sulfate solution was carried out by the current of 0.5 ampere, 0.5 ampere for 20 minutes, or 20 minutes, assuming no change in the volume. What is the pH of the resultant solution? What is the pH of the resultant solution? pH of the resultant solution. Option A, the pH of the resultant solution 1.5, B, it is 3, C, 4.5, D, 6. Here all the options are indicating the solution after electrolysis of the copper sulfate is found to be acidic. Is this correct or wrong? It is correct because on copper sulfate, on the electrolysis process, OH minus ion would be consumed at the anode and oxygen is formed. And the H plus ion concentration is going on increasing. Here you can find out, instead of finding out the OH minus ion concentration, how much is consumed, so much amount of hydrogen would be increased. You can directly work out for what is the equivalent weight of the hydrogen increase in the hydrogen, making use of our problem. Here efficiency of the current is given or not, it is given, therefore no necessity of introducing this. Therefore 1 by 96,500 into I into T, and you can directly put the equivalent weight of the hydrogen, that is equivalent weight of hydrogen, that is increase directly making use of this. I value is given, I think so, 0.5 ampere, and 20 minutes of current is passed, 20 into 60, and convert this. You can calculate number of equivalent weight of the hydrogen that would be increased. You can give this directly. And this increase is taking place in 200 ml of the solution. For 1000 ml, how much is increased? That is equal to the normality of the H plus ion present in 1 liter. From which you can calculate the pH. And of these 4 options, what is the actual one? Work out in the home, and take down the next type of problem that is asked. Ethane is obtained. Ethane is obtained in the Holmes electrolysis. In the Holmes electrolysis of sodium acetate solution. According to the equation, 2CH3COO minus giving CH3CH3 plus 2CO2 plus 2 electron. This is the electrolytic reaction. The volume of the ethane gas obtained at STP condition by the passage of the current of 0.5 ampere within bracket 80% efficiency for 965 minutes is option A 3.45 liter, B 1.8 liter, C 11.2 liter, D 2.69 liters, which is the correct answer. How to approach this problem? How to approach this problem? You are going to see it. Once again, we have to make use of not W should not be used here because volume is given. V is equal to equivalent weight in volume. That is 1 mole would give you 60 and 22.4 liters divided by 96,500 into I into T into X. Why we are introducing X here? Because efficiency is given. I will give you a small hint and then you will complete the problem at home. 80% efficiency, therefore X is equal to 0.8. And equivalent weight in volume. And here methane gas is obtained. Ethane gas, okay. How many moles are obtained? Only 1 mole of gas is obtained. 1 mole of gas is equal to how much? 22.4 liters at STP. Okay. What would be equivalent weight in terms of volume? What is the number of equivalent weight? How to find out equivalent weight for this? You know the formula weight? Ethane is having the formula weight 24 plus சொல்லுங்க பார்க்கலாம். Weight in சொன்னீங்கன்னா 24 plus 630. What would be its equivalent? How to find out, sir? It is in the electrochemical reaction. How many electrons are involved for the formation of 1 mole of methane? Here 2 electrons are involved. Here 2 electrons are involved. Therefore, equivalent weight is equal to the molecular weight by 2. Equivalent weight in terms of gram, 15 gram. Equivalent weight in terms of volume, 1 mole would give you 22.4 liters. Equivalent weight in volume is equal to 11.2. Therefore, in the place of equivalent weight, 11.2 liters. If you put it in liter, we should be also in liter. Okay, into I is given, T is given. You can, what is the unknown? V is not known. Here in the option, all of them given in liter, therefore keep it in this liter. You can easily find out the answer. Okay, you complete the problem in the homework, in the home itself. And the last type of problem, take down the question. This is also a homework for you. Phenol was brominated. Phenol was brominated electrolytically bypassing current through bromide solution. Bypassing current through bromide solution. What is the time required? What is the time required to brominate a batch containing? What is the time required to brominate a batch containing 94 kilogram of phenol? 94 kilogram of phenol. If the strength of the current passed is 20,000 Armstrong unit, 20,000 Armstrong unit. Option A, 1.3 hour. B, 2.68 hour. C, 3.9 hour. D, 5.1 hour. Sir, how to use this? Once again, look at the problem. If whether efficiency of the current is given or not, if it is not given, you can proceed using the formula normal this. If weight is given or volume is given, its weight is given. Therefore, W is equal to not necessary to introduce the X value into 96,500 into I, the strength of the current, and T. What is asked? What is asked? This one is asked. Which one? T is asked. Therefore, you should know the weight of the substance to be brominated. Okay, it is given 94 kilogram, it should be. All right. Then equivalent weight of phenol you should know. Sir, how to find out the equivalent weight of phenol? For which you should write down the equation as it is given in the Holmes synthesis. Here you have to write down the equation for bromination of the phenol. If you write down the bromination phenol equation, you can easily find out the equivalent weight of phenol. Yes, I will work out this one. Before seeing this 94 kilogram, therefore I am writing it in gram. Here I am writing in gram, means here the equivalent weight should be given in terms of the gram. Then this is given, I is given, then T alone is necessary. How to find out? Here the T would be obtained in seconds. Divide the seconds by 3,600, you will get the hour. And equivalent weight, how to find out? Write down the bromination reaction of phenol plus Br2 giving, what is the product obtained? C6, H4, Br, OH, bromophenol. It is a dibromo, tribromo, or monobromo. You should be very, very essential. It is given bromine, phenol was monobrominated. Therefore, I have written it like this, and the remaining is HBr. Therefore, how many bromines are involved in the reaction? It is 2 bromines. What is the oxidation rate of bromine here? 1 bromine, it is elemental state 0. What would be the oxidation state of the bromine in the product side? It is -1. Here also it is having, if you work out it, it is also a -1. Or you write it in this way, bromine is, take that equation alone, it is converted into bromide plus, and it is 2 bromide. Therefore, here 2 electrons are consuming. Therefore, the monobromination of the phenol is a 2 electron process. Therefore, what would be the equivalent weight of phenol? The equivalent weight of phenol is atom molecular weight divided by the number of electrons involved for that bromination. If phenol is sulfonated using this electric current, to write down the sulfonation reaction and how many sulfuric acid molecules are involved in, and what is the change in the oxidation number. You can find out what would be the equivalent weight of the phenol or any organic compound. They can be calculated. Therefore, the phenol atomic molecular weight is 72, 80, 78, and 1694. Here, two electrons are involved. Therefore, equivalent weight of phenol is molecular weight by 2. Therefore, it is given in gram 96,500. I is 20,000 and T in seconds would be obtained, converted into hours. Okay, that is the another problem. You have to work out this. And one more problem I have forgotten, one more type of problem I have forgotten to give. Take that problem also, and with that problem, we finish this electrolysis process equation. Then we go for the conductivity, conductance, so on. Then we will see the application in the conductivity. Calculate, take down the problem, calculate the time required to coat a thin layer of silver on a metal surface area 80 centimeters square, 80 centimeters square, and width or thickness 5 into 10 power minus 3 centimeter. The area of 80 centimeter with the thickness or width I into 10 power minus 3 centimeter. Bypassing 3 ampere current through a silver nitrate solution, within bracket. Density of silver is 1.05 gram per cc. Here, once again, in the electrolysis problem, therefore, what is the formula we are going to use? W is equal to. Here, it is necessary to introduce the X, the efficiency of the current, no mentioning about this. Therefore, we take it to be granted is 100% efficiency into equivalent weight by the 96,500 into I into T. T is asked, therefore I should be provided. I is given, I think so, 3 ampere current. Here equivalent weight of which is a deposited, silver is deposited, therefore what is the equivalent weight of the silver? Take down the formula Ag plus E giving Ag is a 1 electron process, equivalent weight is equal to atomic weight. Therefore, in the place of the equivalent weight, you write it as 108. Here option I have not given, I think so, is not. Take down the option A, 76 second, B, 198 second, C, 126 second, D, 263 second, 263 second. Which is the correct answer? We will see. I is given 3 ampere current and T it is asked. Okay, T is asked. And weight of silver deposited on the metal surface, how much? That is very, very essential. Here, area of the metal to be deposited and the thickness of the metal to be deposited is given. Area into thickness will give you what you will get? The volume of the metal to be deposited. Volume of metal to be deposited. If you just multiply this, you will get the volume of the metal deposited. It would be obtained in centimeter cube. Then one more thing is given, density. Convert this volume into density. Density is equal to weight per volume, isn't it? Then the volume of the metal to be deposited, you have calculated. Density is given. Therefore, you can calculate the weight of the silver to be deposited. Put the value here. Find out the T. Therefore, this is a two-step process. This is also possible to be asked. Okay. With this, I think almost all types of problem in the electrolysis process has been completed. Okay. And the next is the conductivity of a solution, conductivity or conductance. Conductance. What do you mean by conductivity? You know, whenever electricity is passed into the solution through an electrolyte, the electrolyte is present in the solutions. Some of the electrolytes is found to be passing conducting, causing electricity very fastly, and some of them is conducting electricity very slowly. Why they are, some electrolytes are passing conductance very fastly and some very slowly, and research has been carried out on that one in a very long period itself, and if they found that in some electrolytes, when dissolved in water, they are almost completely ionized. And you know, the ions are responsible for conducting the electricity. And those electrolytes in which the ionization is almost complete. Here, look at the word almost, because even the strong electrolyte, depending upon the concentration, some of the electrolytes will not be undergoing ionization. But as a dilution takes place, dilution, the percentage of ionization is going on increasing. You know this. This phenomena is well profound in the case of weak electrolyte. You all know this one. Therefore, ionized, after ionization, it is completely ionized. Therefore, number of ions are present. Therefore, the conductivity of the electricity is very fast. Whereas there are electrolytes in which the ionization is less, and here the ions would be less, and the conductivity would be low. And therefore, depending upon the conductivity, we classify the ions as strong electrolyte conductors and weak electrolytes conductors. And if you plot the conductance versus the concentration, for the strong electrolyte, at most there is a, as concentration, not this much slope, but yes, small slope would be there. Here there is a slight decrease in the conductivity, because as concentration increases, some amount of this, even the strong electrolyte would not be ionized. And if you extrapolate this, the zero concentration, this is we call as the conductivity at infinite dilution. In the case of weak electrolyte, the conductivity is, as the concentration, the conductivity is less, but as dilution increases, the conductivity is going on increasing, because the dilution decreases, the ionization is going on increases. This is for a strong electrolyte, for example, potassium chloride, sodium chloride, potassium sulfate, etc. And this is the case with, say, acetic acid, ammonium hydroxide, etc. This is the conductance, you know this one. And we will see this conductivity and this one, how these conductivities are classified. You are going to define what is meant by conductivity and conductance, and then what are the, depending upon the situation, how many types of conductivities are there. After that, we will enter into the determination of the conductivity. Then going to find out the other things, etc. What do you mean by conductance? Conductance means a general definition we are going to give. The conducting power of all the ions that are present in the given situation. Conducting power of all the ions that are present in the given situation is called conductance. And what do you mean by situations, sir? And depending upon the situations we are giving, these conductance are classified into three types. That is, one is called the specific conductance. Specific conductance. Another is called the specific conductance is represented by kappa. It is just like K, it's a Greek letter kappa, Ka, PPA, kappa. And another is called equivalent conductance. Equivalent conductance. That is represented by lambda C, once again it is a Greek word, or lambda equivalent. The third type of conductance we called as the molar conductance. Molar conductance. Here you should equivalent conductance normality and molar conductance you should give the molarity. That is represented by this lambda m, or some book they represent as a mu c at a given concentration, mu c. Therefore, here the situations are different. Here, what is the situation? How many ions should be present for referring to a specific conductance? And equivalent conductance, and how many ions should be present in the situation? And in molar conductance, how many ions should be present? That is the difference between the specific conductance, equivalent conductance, and molar conductance. And the specific conductance in CGS system, you know what is in base CGS system? The definition is the conducting power of all the ions that are present. This is a common term we have already given for the definition of this conductance. That are present in 1 centimeter cube, 1 cc or 1 ml of the solution. 1 ml of the solution. Therefore, you take 1 ml of an electrolyte. What is its conductance? That we call the specific conductance, represented as kappa. That is K, just like K, but it is just we differentiate from the K, we write it as a kappa. In MKS system, you know the difference in MKS system and this CCS system means centimeter, gram, second. That is length in centimeter, weight in gram, and time in second. CGS system. MKS system, distance in meter and weight in kilogram, and S is the second. Here it is defined as the conducting power of all the ions that are present. That's all the common in 1 meter cube of the solution. Here centimeter cube, but here it is given as the 1 meter cube of the solution. What is the definition for equivalent conductance? Once again, it's a conducting power of all the ions present in, from the name itself, that ion should be present in the equivalent weight of, one equivalent weight of an electrolyte. One equivalent weight of an electrolyte. How many ions are present in one equivalent weight of the electrolyte? That whole conductivity is called equivalent conductivity. Now you are able to define the molar conductance as the conducting power of all the ions present in 1 mole of an electrolyte present in the solution. It is called molar conductance. Okay, this is the first relationship between this definition. Second, effect of concentration. Effect of concentration. What would be the effect of concentration on the specific conductance, on the equivalent conductance, and what would be the effect on the molar conductance? What do you mean by specific conductance? Is the conductivity of the ions present in 1 cc of the solution. And the conductivity depends upon three important parameters. What are the three important parameters? Viscosity of the solution in which the ions are moving. Viscosity. Higher the viscosity, the movement of ion would be restricted and its conductivity of the electricity would be decreased. For example, if you take the sodium ion, it is conducting electricity in water, conducting electricity in alcohol, conducting electricity in an oil, let us assume. Higher the viscosity, the movement of the ions would be arrested. Therefore, in the same sodium ion would be having different ionic conductance in different solving. Therefore, it depends upon this one. Second thing is the temperature. Higher the temperature, higher would be the movement of the ions. Higher the movement of the ions, higher would be the ionic conductance. Therefore, temperature is the second one. Third one is inter-ionic interaction. What do you mean by inter-ionic interaction? The electron is said to be made up of two ions, cations and anions. Cations are moving towards the cathode. Anions are moving towards the anode. While it is passing, a cation will meet another cation or it will meet another anion. If it meet a cation during its passage, cation-cation repulsion. If you meet the anion, it will attract this one. Therefore, its speed will be decreased. If you meet a cation, its speed will be increased. Therefore, this we call it as the interionic attraction. This interionic attraction, in other way, depends upon the concentration of the solution. Higher the concentration, higher would be the number of ions present in 1 cc of the solution. Therefore, interionic attraction would be high. Therefore, what is the effect of dilution? The effect of concentration, instead of concentration, take it to be dilution. What is the effect of dilution? Upon dilution, first effect in the case of specific conductance, the dissociation of the electrolyte increases. Dissociation of the electrolyte increases. Okay. If the number of ions would be automatically increasing, therefore conductance increases. Conductance increases. First condition. And second condition is, as dissociation increases, the number of ions present in the unit volume is increases. Unit volume increases. I'm sorry. The number of ions, here we are going to see the effect of dilution. As dilution increases, the number of ions present in the unit volume decreases, not increases, it decreases. Therefore, the specific conductance decreases. Therefore, what is the ultimate effect of dilution on specific conductance? Generally, it decreases. The dissociation is having a less effect over the conductance than the number of ions present in the after dilution. Therefore, generally, it is decreases. But in the case of equivalent conductance, upon dilution, the conductance is going on increases. So is the case with the molar conductance. This dilution ultimately gives us one parameter called limiting equivalent conductance. What do you mean by limiting equivalent conductance? Limiting means that is the end of the conductivity of the solution. It is either represented as delta superscript naught or delta equivalent superscript infinity. What is this? The naught indicates the concentration is zero. That is, limiting equivalent conductance is the conductance of any electrolyte at zero concentration. At zero concentration, it is not experimentally possible to determine, but it is graphically calculated. When will the concentration would be zero? At infinite dilution. Therefore, instead of zero, we will also put the lambda infinite, that is at infinite dilution. That, that is the limit to the conductance of that particular ion or particular electrolyte. Therefore, we call it beyond that value, that conductivity will never be possible. That limit, we call it as the limiting equivalent conductance. Similarly, there will be limiting molar conductivity, and limiting molar conductivity can also be represented as infinite dilution. This is after the understanding the effect of the dilution. And the next we are going to see what about the unit of the specific conductance, what about the unit of the equivalent conductance, what about the unit for the molar conductance. What would be the unit for this? The unit for this in CGS, in specific conductance, is CGS and MKS system. Two units we have to remember this. The conductance, it is a reciprocal of the resistance of the movement of the ion. You know this. The resistance is given in terms of ohm. Therefore, conductance is given in terms of the reciprocation of the ohm per ohm per centimeter. That is, for the passage of the 1 centimeter, how much is the ohm? It is invert this per ohm per centimeter because it is given in CGS unit centimeter per ohm per centimeter. What would be equivalent unit in the MK system? Per ohm per meter. The per ohm can be reversed like this: mho per centimeter. Just reverse is MHO. Here also it is given as mho per meter. And one more is called Siemen, Siemeen, Siemen, a scientist name, Siemen per centimeter. Here also it is called as Siemen per meter. Siemen is also represented as capital S, Simon or Siemen per centimeter, Simon per meter. And it is this is called the SI unit, System International Unit. And the next question is asked, Simon per centimeter is equivalent to Simon per meter when and where? How? Anybody else? Simon per centimeter. How many Simon per centimeter is equal to 1 Simon per meter? Anybody? Anybody? That can be easily converted. How it is can be easily converted, this one? This centi should not be present to convert this Simon per centimeter to Simon per meter. Here the centi is absent. Therefore, take it outside 10 power minus 2 power minus 1 meter power minus 1 is equal to 1 SC per meter. This is equal to how much? 10 power 2. Therefore, 10 power 2. Here you put this Simon per centimeter is equal to, if you put this, it is converted into this 1 Simon per centimeter. Therefore, 1 Simon per centimeter is equal to 100 Simon per centimeter. is equal to this and these are same. This is the unit for this one, and you should be very cautious in which unit they are giving the specific conductance kappa. Sometimes the per ohm is also the old books, they will be written the ohm as the this what is the name for this, and the per ohm is represented like this also, per ohm. Therefore these are all one and the same. And now we will going to give the unit for the equivalent conductance. What is the equivalent conductance? The relationship between the equivalent conductance and the kappa. The equivalent conductance, we write it as lambda equivalent, and the kappa we written this. What is the relationship between the lambda and the kappa? It is equal to, this is the conductivity of the ions present in 1 cc. It is should be multiplied by a volume V, where V is the volume of the solution, which consists of one equivalent weight of the electrolyte. Here the volume should be in cc because kappa is given in ccml. The volume should also be in cc. We call it as the V is a volume of the solution containing one equivalent weight of the electrolyte. Or you might have studied the kappa into, if a normality is given, 1000 by n normality. You might have studied this. That is obtained, this relationship is obtained from this relationship. This is the equation you should remember so that you can calculate the equivalent weight if normality of a solution is given. Why 1000 is there? The 1000 is for converting this volume in cc. Therefore, we are multiplying is 1000. And what are the unit for this? Here also once again in SI units as well as in the CGS units. Here it is given as, you know the unit for the kappa, you know the unit for the volume, then you can easily give the unit for the lambda equation. Per ohm per centimeter is the unit for the kappa. And what is the unit for this one? So many cc per equivalent, per gram equivalent weight. Or equivalent weight consists of so many cc of the solution. Now join together, you will get the resultant as the per ohm centimeter square per equivalent weight of the substance. Therefore, find the difference between this and this. How this is arrived at? The kappa you know, and V centimeter cube per equivalent. Multiply, you will get this. Therefore, another equation, another unit possible is mho, the same thing, mho centimeter square per equivalent. Another equation possible is Simon centimeter square per equivalent. These are in CGS system, and in the MK system or SI units, here you have to convert this one. Here, in the case of this meter cube, the relationship is change. This is for the centimeter kappa into 1 by 1000 into n. This is for meter cube. Just to reverse this, I am not going to derive this one. Here, this volume in centimeter cube. Here, volume should be in meter cube. If it is in meter cube, this is the equation. Therefore, what are the possible in terms of this meter square? This is in terms of the centimeter, convert into the meter per row meter square per equivalent. And next, mole meter square per equivalent or Simon centimeter square per equivalent. Now our next relationship is Simon centimeter square per equivalent is equal to how much of the 1 Simon meter square, meter square, sorry, Simon centimeter square per equivalent is equal to Simon meter square per equivalent. How much? Once again, as usual, centi should be taken and it should be converted into and per equivalent, etc. If you convert this, you will get this one centimeter square. Okay, tell me how much is there?
10 to the power minus
10 to the power of minus 4 meter square Simon meter square per equivalent is equal to Simon centimeter square equivalent. Right, Tanapa? This can be written like this. Or bring this here, you will get 10 power 4 Simon centimeter square per equivalent is equal to 1 Simon meter square per equivalent. This is the unit for the equivalent conductivity. Now you can easily give me the unit for the molar conductivity. What are the unit for this molar conductivity? What is the unit for this? Per room centimeter square. Only change is there per equivalent we give. Here we have to give per mole. One. Second thing is equivalent to meter square per room meter square per mole. Next is more centimeter square per mole. Here more meter square per mole. And the last thing is, what is the last thing? Simon centimeter square per mole. Here Simon meter square per mole. And you know the relationship between centimeter square per mole and the one, as usual in the equivalent conductance, 10 power 4 Simon centimeter square is equivalent to Simon meter square per mole. This is the unit for this. Next, what is the relationship between the equivalent conductance? Equivalent conductance we have already seen. Molar conductance and the kappa. The same thing as we have seen in the equivalent conductance into 1000 by there in the equivalent conductance we write it as the normality, but here we are going to write it as the molarity. Here, if that is delta M is equal to kappa into V, where V is the volume of the solution containing 1 mole of the electrolyte. Here, if kappa is expressed in centimeter, we should be per centimeter, we should be expressed in centimeter cube, ml. Here also 1 millimeter is given, here also ml. If it is meter is given, you should accordingly change this. This is the equation you have to write if volume is given in centimeter cube. If volume is given in meter cube, then the equation changed is delta M is equal to kappa into 1 by 1000 by molarity. This is a slight change in this one. These are the relationship between the molarity and this. The last relationship is, what is the relationship? This lambda equivalent and the conductance, molar conductance that is given by, as we have already seen, the valency factor. Sir, how to determine this valency factor of an ion? For example, aluminium ion is given, let us assume its molar conductance is given. What would be its equivalent conductance? They may ask you what would be the equivalent conductance, for which you should know. If you just like our uh, equivalent weight and molecular weight determination. Similarly, say lambda m divided by valence factor. What do you mean by valence factor? Valence factor is equal to number of cation, or how many cation is present into the valency of the one cation. Valency of the one cation. If you are given an anion, instead of the cation, you should write it as the number of anion into valency of the anion. You can easily convert the molar conductance into the equivalent conductance. Therefore, this one. Next, we will see the experimental part of the measurement of this conductance. Three types of conductance: specific, equivalent, molar conductance. How they are all determined. After seeing this, next class, there is tomorrow class. We are going to work out some problems using specific conductance, equivalent conductance, and molar conductance, and how to determine the lambda m infinite limiting conductivity equivalent as well as the molar conductance, for which we are going to apply what is this one, that one. Today we will end up our session with the determination of the specific conductance or equivalent and molar conductance. It will take matter of 10 minutes. By 1:05 I will wind up the session. The shell which is used to measure the conductivity of any solution is called conductivity shell. You know the description of the shell, conductivity of the shell. The conductivity shell consists of two electrodes, and it is dipped in a beaker or anything in which electrolytes are there. And these two electrodes are fixed in such a way that the space between them is remaining the same. The space, they cannot be set away from each other. It is a fixed one. The area of this conductor, one electrode, let it be A, and the distance between the two electrode is B, then A into L will give you the volume of the solution confined between the two electrode. That is this. Diagrammatically, I have written this one. In this volume, how much amount of the solution is present? One volume. How much ions are present? They are conducting electricity from one electrode to another electrode. Whereas other ions present in any other way, they are not conducting electricity to this conductivity. Therefore, here the volume of this volume between the two electrodes is kept constant. And the conductivity, as we have seen, is reciprocal of the resistance. Conductivity, let us assume it is the reciprocal of the resistance. And here the resistance is directly proportional. Here ions are moving from one side electrode to other electrode. The resistance offered to the movement is directly proportional to the length of the passage, that is the distance between the two electrodes, and inversely proportional to the area of the electrode. Therefore, you are indebted by A, and removing that the proportionality, you are increasing, introducing the proportionality constant. You call it as the rho. And what is the rho? You define the rho. Whenever any constant is defined, the parameters present, the nearby is taken to be unity. Therefore, rho would be, now it is equivalent to the resistance. Now, rho is called the specific resistance. Why it is called the specific resistance? The length between is taken to be 1 and the area of the electrode is taken to be 1. That is, area should be 1 square centimeter and the length should be, the distance between the two electrodes should be 1 centimeter. Then the volume confined between these two electrodes, 1 cc, and the ions present in that 1 cc is responsible for conducting electricity. That is, we call it as the specific conductance represented as kappa. Therefore, that they give rho is equal to the rho specific resistance is equal to R into A by L. Or resistance is the inverse of the resistance, we call as the conductance, that is kappa. Therefore, 1 by R into L by A, it is we call as the specific conductance because it is a specific resistance is between 1 square centimeter area and 1 centimeter area. Therefore, it's the kappa, and 1 by R we call as the conductance into L by A. For a given cell, the L and A is not can be altered. Therefore, it is called cell constant. L is in centimeter, A is in square centimeter. Therefore, cell constant is always given in terms of per centimeter. And the conductance is reciprocal of the resistance. Therefore, the C is having the value per ohm and per centimeter. What is this? Is the unit we have already given. Therefore, dipped into the conductivity shell into the electrolyte, find out the conductance of the solution, put C and multiply with the cell constant, you will get the kappa. That is specific conductance. Therefore, thus the specific conductance is determined. And next, how can the specific conduction of the electrolyte is determined? It can be converted into equivalent weight of the electrolyte, lambda of the equivalent weight of the electrolyte as kappa into 1000 by the normality of the solution. This is in terms of lambda per ohm centimeter square per equivalent. 1000 would be placed below this in the denominator if you want to calculate it in terms of per ohm meter square per equivalent. This is the calculation method by which we can do problem tomorrow. And next we are going to calculate this one, lambda equivalent and lambda per m. What do you mean by this? Equivalent conductance as well as the specific conductance. How is it possible to calculate the equivalent conductance or specific conductance, for which we are going to use the DHLL method? You know this one. What is DHLL term? Differential லிமிட்டிங் லா அப்படின்னு சொல்லுவாங்க, டிஹெச்எல்னு கூட சொல்லுவாங்க. differential limiting law method. That method is the equivalent way conductance or the molar conductance of any solution would be equivalent to lambda naught, that is the equal limiting equivalent conductance or molar conductance, minus K. A K is a constant into root C. C is the concentration of the electrolyte. This is the equation you have to use to calculate the equivalent conductance for a strong electrolyte. For a strong electrolyte. Here I am not going to derive this differential limiting equation. You are well familiar with this. And then for weak electrolyte, you can't make use of this equation for which a separate equation would be available. That separate equation is 1 by lambda equivalent or molar conductance of weak electrolyte is equal to 1 by lambda naught equivalent or molar conductance plus equivalent bar molar conductance divided by infinite or limiting or equivalent and molar conductance. Where this equation is not, I am not going to derive this one, and I think you are well familiar with this one. The C concentration by Ka or Kb, where Ka you know the acid dissociation constant. If you put it as a Kb, it's a base dissociation constant. This is the relationship you can make use of for calculating the lambda equivalent conductance or molar conductance for a weak electrolyte. And making use of this, how would you calculate these ones or experimental determine? As usual, determine this, take the specific conductance of the solution using the conductivity shell and making use of various concentration. You can calculate this and this using the kappa into 1000 by N normality R divided by molarity, you will get the equilibrium. For various concentration, prepare this lambda, this value, and plot this lambda equivalent per molar with respect to root C. This is in the form of Y is equal to mx minus Kc. Now you will be having one straight line with a negative slope from which you will be, I'm sorry, Kc, it's not Kc, mx, sorry, it is in the form of C minus mx. You will be getting the lambda naught experimentally. Similarly, you can, what is the variable? This is a variable in this side. This is a constant, this is a constant, and this is a constant, and these two are the variables in the other side. Therefore, you plot it for the weak electrolyte also, you are getting a straight line. From the straight line, you can find out this one, that is limiting conductance. For a strong electrolyte, which should be plotted against which one? Lambda equivalent conductance or molar conductance with respect to root of C. You will get a straight line with a negative slope. Therefore, you will get a like this. When the zero concentration and the concentration is going on in increase way, and extrapolate to the zero concentration, you will get lambda naught equivalent or the molar conductance. This is for the strong electrolyte. If you plot the same for the weak electrolyte, you won't get a straight line for the weak electrolyte. It will be just like this for weak electrolyte. Therefore, we have derived an equation for the weak electrolyte, and in the weak electrolyte, you have to calculate plotting 1 by lambda or the equivalent or the molar conductance with respect to what are the variables we have seen, the concentration into lambda equivalent conductance in lambda, you will get a straight line. But here straight line is here positive slope. And if you extrapolate it to the zero concentration, you will get the 1 by lambda naught, the limiting conductance for the equivalent and molarity. What is the slope of this straight line in the case of strong electrolyte? That is nothing but minus k. Minus k, what is minus k? K is a constant. This will be, we will discuss when we will discussing the de Onsager theory. Okay, at that time we will discuss what is the k, how to arrive at this, and what is the slope here. What is the slope here? And if you find out the slope here, the slope is nothing but 1 by lambda not equivalent conductance or molar conductance into Ka. Therefore, you should remember this. Sometimes some question may be asked when you plot this and this, which is the correct representation, graphical representation of a weak electrolyte, this one, this one, this one. When you plot this one, which is the correct way of you should be able to give this one. And this by this method, you can determine the lambda naught also experimentally. But this lambda naught is theoretically calculated by Gold-Ross equilibrium or molar conductance can be calculated using Gold-Ross law. What is Gold-Ross law? We will see it tomorrow. We will see it in tomorrow. And after seeing this Gold-Ross law, we will work out some problems in these conductivity measurements. Then after seeing this, we will be going for ionic mobility. Therefore, tomorrow's menu would be this Gold-Ross law and the applications of the Gold-Ross law, then ionic mobility. Okay, thank you.